Hello again, my dear students. We will continue on the topics that we did go through in the early morning today. So once more, he is asking you to verify that the function, this function, which actually maps R3 into R2, is differentiable at the point 0, 1, and e. And he wants you also to calculate the Jacobian matrix of this function at the point 0, 1, and e. So let's start our discussion. So this function mainly forms of two functions, or it will map x, y, and z into two values or two functions. The first of them is x squared 3y plus ez. The second is sine x plus line y and z. First thing to do in order to check the differentiable, that this function is differentiable at the point 0, 1, and e, I will do something really very simple to verify the differentiability. We will check that all partial derivatives of this function already exist and they are continuous near this point. What I remark for the first function, which is x squared 3y and e to the power of z, it's simply a smooth function, actually contains polynomials, linear functions, and exponential. So this function is actually continuous and the partial derivative exists at everywhere. In a similar manner for the second function, it's vice versa. You have sine of x, which you have no complications whatsoever with this trigonometric functions. And we have the other function, which is a logarithmic part of, or logarithmic function of y times z. So all I have to check is y times z within this point already has no problems with the logarithmic function or greater than 0, which is really very simple, because when you look to the point that we are performing our discussion about the y value is equal to positive 1 and the z value is e, so 1 times e, you will end up having e, which is a value greater than 0, so there is no problem whatsoever with the second function. So for this function, as we studied previously, for a function to be sure that it has no problem with the differentiability and the partial derivatives exist, I should be aware that I should check for all partial derivatives. For two functions, for these two functions, the first and the second, we have no problems whatsoever near the point 0, 1, and e. What's remaining to be evaluated is the Jacobian matrix. Of course, we have two functions, and as we saw in the first lecture in the morning, that we have three variables. So we will have the Jacobian, it's gonna be of 2 rows and 3 columns. And I will start getting each one of them. So differentiating with respect to x, you will have 2x. Differentiating with respect to y for the first function, it's gonna be 3. Differentiation with respect to z for the first function, it's gonna come up to e to the power z. For the second function, in a similar manner, giving the x value, it's gonna give you cosine of x. Giving the y value, it's gonna be 1 over y and z times z, which you will end up having just only 1 over y. Similar manner with the z value. So here is the Jacobian, f1 with respect to x, y, and z, f2 with respect to x, y, and z, as you can see. And here we go, that's the first, second, and third derivatives for the first row. And once you start substituting with the point 0, 1, and e, I will replace x with 0. Here y will stay as it is, there is no y value. And for the z, it's going to be e, so it's e to the power of e. In a similar manner, you will have f2 differentiated with respect to sine x will be differentiated. For the y and z, you will have similar values, so there is no problem whatsoever with respect to the second guy. Okay, now I will start substituting with the values 0, 1, and e. And here is the Jacobian at 0, 1, and e. Very simple, smooth, very simple problem. What we need to discuss at the time being is not complicated, but it's an urgent matter. How to differentiate composite function in more than one variable or in multi-variable functions. If you remember, for the first, for in one dimension, if I have composite function, for example, if I have f of u and u is a function in x, simply, or u is a function in x, all we have to do is to getting first partial or getting the derivative of f with respect to u, then multiplying by du with respect to x. So this is mainly how we do the derivative of getting the df with respect to x in the case of one variable problems. For example, if I have, for example, cosine of an x squared plus 1, you used to do the derivative, this is y, so you are getting y dash, which is going to be simply a negative of a sine of x squared plus 1. That's the derivative of the main function times the derivative of the function or the argument inside this one. So you simply multiply by 2x. Now what's going to be the case since the derivative is the Jacobian? So once you do a composite function derivative using the multivariable functions, you will need to know about the Jacobian of composite functions. In general, the Jacobian of composite functions is really very simple. All I have to do is to do a multiplication for two Jacobians. The first one, which contains the second function, times the Jacobian of the second function. So, to make it much easier on you, if I have h, for example, which is f composite g, it's the function of f composite g. If I want to find the Jacobian of h, it's gonna be simply getting, this is f inside g of x inside of f. I will have to first get the Jacobian of the f function of g of x times the Jacobian of g of x. These are the two Jacobians required in order to go through a derivative in composite functions in multivariable functions. Okay? So, once more, if I need to get f composite g, I will have to get the Jacobian of the outer function. Then, I will make the replacement with the g of x times the Jacobian of the interior function. Okay? So, it's really very simple. And all of this is stated right here. So, now once more, if x of t is differentiable at t naught, y of x is differentiable at x of x naught, then the composite function y of t equal y as a function x of t. I will differentiate the first function, then I will differentiate times differentiation of the argument. This is mainly the rule that we use in composite functions in one dimension. Once we go into multi-variable space or to a function in several variables, the process will be just only depending on the Jacobians as I told you. I believe it's better to have it on a problem or an example. It will make it much easier and easier to understand. But before doing so, I want you to understand the concept of the composition by itself. In multivariable functions, okay, this is the here, for example, I can get f, okay, composite g, but I can't get g composite f for this problem. Simply because if you look closely to the function f, the function f maps elements from Rm into the result, or the output will be Rn. So the function that should go inside f should actually give Rm. So if I want to get f composite g, it is workable. Why? Because g by itself maps elements from Rn, and the output of this function is going to be m. Okay? Why? Once you get to enter the function of f, the input should be an n, so these two guys should equal to each other. The output of the inner function should be equal to the input of the outer function. Okay? But if you replace them, getting G composite F, it's not going to work. Because simply, and that's the general case, because simply F will map stuff into R to the power of B or into a B space. So that's the output, which is B space. Once you use F and you try to insert it inside of G, it's not going to work. Because simply G starts or needs an input of n variables. Okay? This is something should be checked while you are making composition of functions on your own program. This is G of X, as I told you, it's an n functions, n variables, and that's the Y, same way like for the function. That's the composition that I'm telling you about. That's the law. I will get the Jacobian of the outer function, and then we'll do the replacement through G of X times the Jacobian of the interior function. Ibrahim, be with me, please. Let's go through this problem, step by step. Okay, he is telling you, number one, you have two functions. What are the two functions? What are the two functions? The first function is G, mapping stuff from 2 dimension into another 2 dimension. So it's taking X and Y and mapping them into X squared plus Y and X times Y. And for the other guy, which is the function F of U and V, also takes elements from U and V and they map them into U plus V squared EU time plus sine V. Okay? So these are the two main functions. Now, I will need you to get the Jacobian of G. I will need you to get the Jacobian of F. And I also want you to get the Jacobian of H, where H is F composite G. Now I will get to the point of getting a Jacobian of a composite function. So let's start step by step. First of all, I will try to get the Jacobian of F. This is the Jacobian of the F function. So let's concentrate all together and start getting this file. Okay, I will need the Jacobian of the F function. What's the F function? Okay, it's a U plus V squared EU sine V. So simply, all I have to do is to get partial F, partial U, partial F, partial V. And this is for F1, the first row. I will do exactly the same, but with F2. So it's partial F2, partial U, partial F2, partial V, which is gonna equal. Here we go. Start differentiating the first row with respect to U. So with respect to U, it's gonna give you 1. Then with respect to V, it's gonna come up to 2V. Okay, for the second row, differentiating with respect to U, it's gonna be e to the power of U. Here we go. Then differentiating the second function with respect to V, it's gonna come up to cosine over V. So that's the function. 1, 2V, e to the power of U, cosine V. Very simple. Any problems? Any questions? Huh? Here we go. Okay. Now I will get the Jacobian of G. That's the Jacobian of G. Once more, I will go to the G function, which is X squared plus Y, X and Y. I will start differentiating the first function, which is X squared with respect to Y with respect to X. So it's gonna come up to 2X. يا شباب, انتوا معايا?
2x
Differentiating with Y, it's gonna be 1. For the second row, differentiating with respect to X will give you Y. Differentiating with respect to Y, it will develop X. So that's the Jacobian of G. Now I will have to find the link between them. Remember, once more remember, that I'm getting the F of G of X. So the output of G is gonna be the input of F. Which means, what's the output of G? X squared plus Y. Which equal to the input of F. Which stands for, which means U equal x squared plus y, and the v equal xy. That's a link between them in the composition. Once more, I'm getting h. H here is f composite g of x, which means that output of this guy, of this function, which is g of x, is gonna be the input of the f function. The j function output is x squared plus y and xy. The input in the f is gonna be u and v, which means that u equal to x squared plus y, and the v, you guys, is gonna equal to xy. Now, I'm going to get the Jacobian of g, okay? I'm sorry, the Jacobian of f composite g of x, which is gonna be simply, the Jacobian of f times g of x, times the Jacobian of g of x, that's the Jacobian of the composite function h, which is f composite g. All I have to do now is to start substituting. So getting the Jacobian of f of g of x, I will go to the Jacobian of f. That's the Jacobian of f. Start substituting instead of u and v. So it's gonna be a 1, then an x times y, then e to the power of x squared plus y, then I will have cosine xy. This guy will be multiplied in the Jacobian of the G matrix, which is simply a 2 over xy, y and the x, and then start multiplying these two matrices as you talked previously in linear algebra. Do you know that? It's really very simple. I will start multiplying the first row by the first column and so on. Okay? تمام 100. Okay. Now let's do it once more. So get the Jacobian of G, get the Jacobian of F. Each one of them is evaluated in details. Then we will get to the Jacobian of the H function, which is the composition of F of G, where H is equal to F composite G of X. The first step, as we saw, I will get the Jacobian of G. So once more, G maps R2 into R2. So now I will get G1 with respect to X, G1 with respect to Y, similar manner, getting G2 with respect to X, G2 with respect to Y. Here's the J function, start differentiating. So here is 2x1, Y and X, and it's exactly as we saw. Similar manner for the function for getting the Jacobian of U. I will start doing the same, but with the f function, which is u plus v squared, u plus sine of v. Doing this exactly will leave you with this guy. This is the end of it, 1, 2v eu cosine v. And here we go. Here is the function that we are talking about. Once more, I'm interested in getting f, I'm getting h, which is f of g of x. So the output of the g of x is going to be the input of f. So all I have to do is to make the substitution at the time being. I will consider these are the results that we reached. Here, our guy, I will need Jacobian of f at the values of g of x or y. The output of g, which is going to be the values of the functions illustrated previously, x squared y and xy, it's going to be the input of the f function, which means that u will equal to x squared plus y and the v equal to xy. Making the replacement, this is the function or the Jacobian of f of g of x. Here we go, 1 xy e to the power of x squared y cosine xy, exactly the same. Then I will multiply them both together. Here the two guys, multiplying this matrix times that matrix. It's really very simple, a piece of cake. And now you will have, this is your final answer for the Jacobian connecting them. Brahim, why we do all of this? Brahim, if I have cosine x squared, can you differentiate it, please? Cosine of an x squared.
-2 sine.
Wait, step by step. It's going to be a negative sine of an x squared. Then times 2x, am I right? Yeah, okay. So the first derivative, you already differentiated the outer function. The second part, or you multiply it in the derivative of the inner function. صح؟ It's exactly the same. هو بالظبط. أنا لما باجي أعمل derivative لفانكشن جوه فانكشن بجيب الديريفاتيف الأول بتاع الأوتر سيرفيس.
But since it's multivariable function itself, we have to use the partial
Jacobians. We have to use the Jacobians. And that's it. Okay, very simple. Here we will start talking about if I have parameterization for a function as a function in T and so on. Okay, this is very, very interesting. If I have Z as very interesting and not confusing, but it has very nice taste. This is Z, which is a function in X or Y. Both X is a function in T and Y is a function in T. So if I want to differentiate and getting a Z as a derivative in T, don't do it.
يا ميدو.
اختفى. Gone with the wind. Gone with the wind. قعدت اقول فين يوسف. يوسف disappeared.
يوسف فقد الامل. على فكره لما ماسكين في محمد، هو محمد هو اللي هيلم لهم المنهج. هاي بس احكم في السؤال.
محمد قدامه هدوء طبعا. طبعا.
سندال فعلا بالله.
خلي بالك ان Z is a function. هنا انا عندي Z is a function in مين ومين. شباب انا عندي Z is a function in X و Y. اوكي اول ما نخلص نقعد عشان انا عايز اضحك. اما يبقى عندي Z ده function في مين؟ X و Y. هو X by itself is a function in T and Y is another function in مين؟ in T. انا عايز اجيب مين؟ ده التشين ثيوري. انا عايز اجيب مين؟ عايز اجيب دي زد باي دي تي. طيب هعمل كده؟ يس. So it's gonna be partial z partial x then plus partial z partial y. So I will have to differentiate the main function, which is z, to its main two variables, which is x and y, since both of them are functions in t. Then I will multiply here by d of x times dt or by dt and define the derivative of y with respect to t. And that's the chain rule, or in the case of having a parameterized function as x as a function of t or y function of t. And here we go. That's the derivative of z with respect to x, the derivative of z with respect to y. Then, Ibrahim, I will multiply dx by dt and dy by dt. That's the first branch, and that's the second branch. What if the function x by itself is a function in several variables? So I'm getting z in function in several variables, and also x as a function in several variables. If I want to see a simple application on this law, it's going to be like this. You will have now z as a function in both x and y. And the x is given by cosine theta, y is given by sine theta. So it's really very simple. All I have to do is to differentiate simply this guy with respect to x, which is going to be a half times xy plus y to the power of negative half times y. Then I will differentiate it with respect to y, which is going to be once more 1 over 2 times xy plus y to the power of negative half, but this time it's going to be times x plus 1. And that's the derivatives of the main two branches. Partial f, partial x, partial f, partial y.
Why don't we
Okay.
just substitute with the
Let's do it step by step. I know what you are saying, but this is the rule if it is getting more complicated than this. It's just training you in this rule. I know what you are saying. I can simply, and I love to do this by myself. Instead of going through all this, all I have to do is just replacing x by cosine theta, y by sine theta, and I can manipulate the trigonometry, and same way for y. Yes, you can do that. But here it's an application on this theory because of introduction for multivariable functions. Okay?
Yeah,
So,
the
all I
easier
have
one-
to...
The easier one is by substituting for this case. But generally, the chain rule is easier.
Yes. Yes. But you can do whatever you want to do. Okay? Okay. على طول أول ما أبدأ أشتغل فيها لا if accessible for you. Because sometimes it's not going to be that easy as you will see. Okay, let's start with getting partial z partial x, which is going to be very simple. It's going to be 1 over 2 root x y plus 1 times derivative of 1x, which is simply y, times I will leave a room for dx by dt. Then I will go to the second branch, which is partial z partial y, which is going to be simpler. Okay, I'm sorry, exactly the same way, which is 1 over 2 over x squared plus y squared, as you can see. Then I will differentiate what's the values of, sorry, it seems like from repeating this guy, stuck in my head, xy plus 1. Then I will start to differentiate with respect to y. With respect to y, you will have x plus 1, and also times partial dy by dt and dx by dt. Differentiating with respect to t is really very simple. So dx by dt is going to give you, or by d theta in our case here, so it's going to be a negative of a sine theta, and for differentiating y, it's going to be a cosine theta. Then I will replace x and y by the values cosine theta, sine theta, if you like, and I will have a function of theta, which is very, very simple. Here we go, once more. That's the law, partial z, partial theta, partial z, partial x, partial z, partial y, times partial x, partial theta, partial y, partial theta. And I will start substituting in a similar manner. So, getting the first derivative with respect to x, partial x, partial theta, the first derivative of z with respect to y, then dy by d theta, which is cosine y, multiplying all together. Then I will do the replacement by sine theta, cosine theta, and I will have the final form of this function. This rule can be generalized. As you can see in the coming slide, here we have a function in x and y. And the x by itself is a function in u and v. And the y also is a function in u and v. So if I want to get the derivative of z with respect to u, I will have to use the partial derivative rule, okay, in order to get this, guys. And that's the tree diagram if you want to do it like this. So I will start differentiating z in our, first with respect to x, with respect to y. Then getting for x, I will start, if you need to find the derivative with respect to u, I will multiply in the partial x, partial u, and so on. It's a generalization for this one. Okay, let's do this for this problem. I have an f, which is a function in x squared plus 3y, and we have the following. That's g, s and t, s, which is plus 2t, s squared minus ln t. Which means that if we want to find f composite g, it means we are going to use the chain theory. Okay, so I need to find partial f composite g with respect to s, partial f composite g with respect to t as functions in s and t. That's the simple diagram. I usually don't follow it. I like to write my stuff directly. So now, if I want to do this rule or to find these derivatives, it's very, very simple. And it's exactly like the problem that we saw earlier. So all I have to do is to start with this. I need to find partial f and partial s. So all I have to do is to differentiate f with respect to its main variables. Main variables start f. يبقى partial f, partial x, then partial f, adding two branches بتوعها. بعدين الاكس is a function in s and t. يبقى إذا times partial x, partial s, times partial y, partial s, as you can see. If I want to do it with respect to the other variable, it's going to be exactly the similar. These two guys will remain the same, but here it's going to be partial x, partial t, and this one be partial y, partial t. So it's really very simple. Here we go. That's the composition. Okay, I will need to differentiate partial z, partial s. So I will differentiate z with respect to x, partial s, partial z, partial y times partial y, partial s. Direct substitutions from the part of the function and from the other two guys. Here we go. That's the derivative of z with respect to x is going to be 2x. Derivative of f with respect to y is going to be 3. Here is the 2x, here is the 3. Differentiation with respect to s is going to equal 1. Okay, and the differentiation with respect to s for the y component is going to be a 2 of an s, exactly like this. So that's the final result. It's very simple, but a little bit confusing once you start to get the results out of a multiple choice question. Here is with respect to t, exactly in a similar manner. Once more, differentiating z with respect to x and respect to y, then differentiating with respect to x with respect to t, differentiating y with respect to t. What if we have the case, this is also another problem before going to further cases. This is for z, which is a function in u squared plus 3v. And here is u, x squared y, and here is v, is xy, and e to the power of y. If you need to find partial z, partial x in a similar manner, it's going to be partial f, partial u, times partial u, partial x, simply like partial v, partial f, partial v, times partial v, partial x. Just direct substitution of these functions. I've added these examples for you to make your life easier once you are training yourself in getting these partial derivatives. It's really very simple. All I have to do now is to make the substitution and you will have the final answer. It's very smooth and very simple. Done. Now compute the partial derivatives of x and y. Also, same problem, but with respect to y, so it's going to be exactly the same. There is no problem with that. Any questions for this part? Okay, here we go again for the chain rule, but in less than touch. Here is x, u and v, y is u and v, z, u and v. So now I'm talking about x, y, and z, and the x, one of them, and each one of them is a composition of u and v. So your rule is going to be exactly the same. I will differentiate z with respect to its variables. So it's going to be partial z, partial x, partial z, partial y, partial the function with respect to z. Then multiplying whatever it takes or whatever each part of them by the value that you want to do. partial x, partial u, partial y, partial u, partial z, partial. شباب بتفهمين بقول ايه؟ عايزه تفتي كده. لو انا حطيت لك الاف فانكشن، شفت الاف انا اديتها لك از فانكشن مين ومين؟ اكس وواي. والاكس كان فيه يو في والواي كان فيها يو في. فبطبق التشين رول، بس عندي كام برانش؟ 2 برانشز. بمسك الاف بارشل اف بارشل اكس بارشل اف بارشل واي، بعدين بضرب في اللينك. بارشل اكس بارشل ثيتا اللي هو في ار ثيتا، والتاني بارشل واي بارشل ثيتا. طيب لو انا عندي في 3 دايمنشن يبقى عندي الاف فانكشن او الفانكشن بتاعتي هي فانكشن في مين ومين ومين؟
اكس واي وزد.
والاكس فانكشن في ار وثيتا، والواي فانكشن في ار وثيتا، والزد فانكشن في ار وثيتا مثلا. عشان كده بروح مقسمهم على كام؟ على 3. هديفرنشيت الاول الزي مره بالنسبه للاكس، مره بالنسبه للواي، مره بالنسبه للزد. همسك الاكس اروح اعمل بقى تاني ديريفاتيف واعمل مالتيبيكيشن بارشل اكس بارشل سي. بعدين البارشل واي البارشل اف بارشل واي اروح ضربه بارشل واي بارشل سي. البارشل اف بارشل زد اروح ضربه بارشل زد بارشل ثيتا اند سو. اذا كان ار وثيتا واذا كان يو في جاست جنراليزيشن اوف ذا رول، فمفيش اي بروبلم واتس ايفر. خدها معانا. ايه رايك؟ لذيذه مفيش فيها حاجه. فرق كده انا عندي اليو فانكشن في مين ومين؟
اكس وواي وزد.
قشطه. وانا مديك كمان الاكس فانكشن في مين؟ في ار واس ودي. ايه اللي فارق معاك؟ انا عايز اجيب بارشل يو بارشل ار. هعمل ايه؟ همسك بارشل يو بارشل اكس زائد بارشل يو بارشل واي زائد بارشل يو بارشل زي. بعدين اروح جاي قايل له تايمز بارشل اكس بارشل ار بارشل واي بارشل ار بارشل زي بارشل ار. في مشاكل في كده؟ ها معايا؟ بس كل اللي هيفرق ان انا هكتر بقى الديريفاتيفز بتاعتي بس. يبقى اذا هروح اجيب بقى اهو بارشل يو بارشل اكس differentiate with respect to x it's gonna be 4y x cube. بعدين هضرب في بارشل اكس بارشل ار هيديني اس في اي تو ذا باور اوف تي. اللي بعدها زيها واللي بعدها زيها واللي بعدها زيها اهو ستيب باي ستيب. هير وي جو. بارشل يو بارشل اس لو انا مش هعمل لار هعمل لاس هيبقى بارشل يو بارشل اكس بارشل يو بارشل واي بارشل يو بارشل زد. بعدين يلا بارشل اكس بارشل اس بارشل واي بارشل اس بارشل زد بارشل اس. ستارت سبستيتيوتنج. هوجد البارشل ديريفاتيفز واعمل سبستيتيوت.
حضرتك هتكتب ار ليه هتكتب ار؟
لان انا بجيب بارشل يو بارشل ار كنت شفت ان هو عايز اس.
عشان كده انا عمال بحل على
طيب خلاص تمام كده؟ خلاص ابدا اعمل بقى بارشل يو بارشل اكس هيدي لك 4 واي اكس كيوب اهو انا كتبتهم هنا الاول. ده بارشل يو بارشل اكس بارشل يو بارشل واي ده بارشل يو بارشل زد ادي بارشل اكس بارشل اس بارشل واي بارشل اس بارشل زد بارشل اس. بعدين هعمل لهم سبستيتيوشن ادي الشكل بتاعهم وهعمل كمان سبستيتيوشن مكان اكس وواي وتطلع كلها فانكشن ان ار بس. تمام؟ اوكي. برضو another example هو مديلك هنا الاف اوف اكس واي دي حاجه مختلفه شويه. هنا بيقول انا مديلك الاف اوف اكس واي as a u function و v function. اليو فانكشن هي اكس زائد واي والفي فانكشن اكس ماينس واي. يبقى انت كده عارف انه الاف فانكشن بتعرفها ازاي باكس باليو والفي وكمان الاكس زائد واي والاكس ماينس واي. كمان مديك الجي والجي دي يو في مين؟ في في. وهنا يو تايمز في هنا يو سكوير ماينس في سكوير وهنا مين؟ وهنا الفي. يبقى انا مديك الاف ومديك مين؟ الجي. بص بيمابس ازاي؟ خلي بالك ان ده بيماب 2 into 2 ودي بتماب